Hello everyone, I'm Yunjie, girl from Wuhan University, and it's my pleasure to be here to present our work hijacking attack against the neural network by analyzing training data. Our work focuses on the deep neural network, or DNNs. As we all know, DNNs have two important stages, the model training and the model inference. But during these two stages, DNNs often face two well-known threats such as the backdoor attacks and the adversary attacks. Next, I introduce the attacks. Backdoor attack takes place during the training phase, where the attacker can modify either the training data or the code to install that backdoor into the DNNs. And then the attacker can use the trigger to manipulate the output to produce the error result. This approach has the advantage of the high attack success rate, but they require the strong deception about the attacker can tamper with the model's training data or the process. On the other hand, adversary attacker, also AE attacks, usually take place in the inference phase, where the attacker prefers the noise to manipulate the output of the model. So these attacks are more practical because they could operate under the exception when the attacker has no access to the training process. But they are usually will suffer from the low attack success rate when the model is blackboard. So our research question is, can model hijacking be achieved with a higher attack success rate and a more reasonable exception? In our study, our threat model assumed a blackboard scenario where the attacker has zero query and zero poisonous capability to the model, but he can obtain some knowledge about the training data. This will include the scenario like the open source data leakage, fine-tune model, and so on. Let me introduce the insight behind our work. We observed that the neural network will highly rely on their robust feature for classification. Here is an example. The DNNs will recognize the image of the elephant based on their robust feature, like their noise. What is well, if the future can be manipulated? For example, if image cat will inherit the elephant's future, what would happen? The model will think the image as elephant because the image contains the future of the elephant. So this means the future can be utilized to attack the model. So this inspires us to exploit with what we call nature backdoor. This means the backdoor is not installed by an attacker. So we first consider the typical data poisonous backdoor attack. The attacker can paste a trigger in the image and label it as the target class. During the model training, the model will learn an error connection between the trigger and the target label. So for clean training data, we could observe that different training data will show the common information like the robust future. So the model also will learn a connection between the robust future and the true label. We found out there is a very similarity between the poisonous data and the clean data. So we think the training data can be viewed as a kind of poisonous data. Therefore, they will introduce the nature backdoors. In other ways, the attacker also can utilize the nature backdoor to control the model, but rather than installing a backdoors. So another question is raised: how to extract the robust future as a trigger for DNNs? Since the model learns the information from the training data, so we think we also can extract the robust future from the trained model. Moreover, to successfully hijack the model, we think the trigger should satisfy the two basic conditions. The first one is the hijacking usability. This means the trigger should have the ability to, for the model, The second one is the invaluable example invariance to ensure the effective of the attack in the real world. The trigger should not alter the classification of the human, also are required by the existing backdoor attacks. Thus, we formulate the problem of generalizing the natural backdoor trigger as a multiple objective optimization task. Aiming, the first one is to ensure the hijacking usability. The second one is to ensure the example invariance. However, we found that since the attacker cannot access to the training and the inference process, so it is very challenging to solve this question in a blackboard setting. A simple solution is to train a local model or a substitute model, use their gradient to address the question. But we found that the trigger generalized on their substitute model and not always can successfully attack the target models. So we attribute this problem to two reasons. The first one is the substitute model may suffer from overfitting, so they fail to learn the class-related features. The second one is the different model will learn the different class features. Therefore, we proposed to use the chronology dissertation to enable the substitute model to learn more correctly and use the model agnostic first to extract the common feature among the different models. To enable the substitute model learn more effectively, we integrate the comparator of competitive learning. Here we first generalize modify the substitute model and select the best performing one as the teacher and to tutor other substitute models. And to avoid the problem of difference between the extracted feature from the substitute model and the learned feature in the target model, we propose to use the inner and outer loop merge. In the inner loop, we generalize the trigger for the first model and use this trigger as a base to generalize the trigger for the next substitute model and go on. So this trigger will contain the robust feature of each substitute model. In the outer loop, what we need to do is upgrade this trigger to generalize a new global trigger. Since this new global trigger will capture the robust feature from the all substitute model, it will have a greater chance to attack other models. So please refer our paper to get more details. To evaluate our approach, we conduct the experiment across the modified dataset, including CIFAR, ImageNet, and with a total of 79 normal chain models. We only used the for substitute model to generalize the natural backdoor trigger, yet the advantage attack success rate ASR is across the different dataset and models often over 19%. For ImageNet dataset, we only used the data of the first 100 classes to train the substitute model. However, it still achieved about 17% ASR on the model trained on 1,000 classes. Ours also achieved a high ASR in the audio or the speech recognition models, proving the generality beyond the ImageNet. Here we assume the attack only have a preparation of the train data or no data from the train set, but can update some data with the same distribute at the train set. In our experiments, we displayed this 4 train set into 10 subsets, used the sum of them to train the substitute model and the remaining to train the target models. Based on the result, we can find that although the attack have the chronology of the distributor of the train data, the attack is successful. Moreover, we consider that the attacker neither the data from the train set near the data with the same distributor. Here we divide the dataset into 2 subsets, which satisfy the non-ID settings. Based on the result, we can find that the ASR still has 19%, and the disgrace is minor. We believe this is because the data from the C classes by the different distributor still show the similar reversed future. For example, imagine with the bad elephant always include the reversed future like the else and Chong. Thus, our attack can work as long as the attacker can capture the reversed future of the target class. Finally, we would like to make a summary of our work clean shared. Clean shared work in an offline manner without the need to modify the training data and algorithm or access to the target model. Trigger generalized for specific target model can also be utilized to attack other blackboard models. Last but not least, Clash assured comparable performance to state of the backdoor attack, but rely on more weaker exception. That's all. Thank you for listening. I'm ready to get a question.